The next thing we're going to need to look at is how we can analyze motion using all the kinematic variables. So up till this point in time, we have equations that relate velocity and displacement, right? Velocity equals displacement over time. We have equations that relate acceleration. Acceleration equals change in velocity over time. But we don't necessarily, as of yet, have any equations that can relate displacement and acceleration, or acceleration, velocity, and displacement all in one equation. So the way we can do that is using what are known as the kinematic equations. Now these kinematic equations are derived from graphical analysis. So as we'll wrap up the graphical unit, or graphing motion unit, it's a good point to at least explain how we get some of them. Now deriving some of the kinematic equations, there's generally four. I show five in the class. One is just a rearrangement of another one, but I like to demonstrate in that way, and you'll see why momentarily. I'm going to go through quickly two derivations, so how we get two of these kinematic equations from the graph. I'm not going to go into all five because I don't necessarily think understanding how to derive all of them is vital, but I do think that realizing that they are obtained through graphical analysis is important enough to at least show you how two of them are derived. So if we take a look at this velocity time graph, the red line represents the actual graph. I've drawn in these dotted lines to represent these two different shapes. I've also shown you that this is technically the final velocity and this is your initial, because this is the velocity you begin with and this is the velocity you end with. So hopefully you realize I have some initial velocity. This is accelerating because I'm increasing and I wind up with a higher final velocity over a given amount of time. If you remember slope-intercept form, y equals mx plus b, where y and x are the x and y values, m is the slope, and b is the y-intercept, or where that line crosses the y-axis when x equals 0. Okay? All we have to do is take a few of the concepts we've learned. We know that the y value is actually the final, right? Your final y, whatever you calculate, you plug in some x, you'll get a y value. That will be your final velocity, because at whatever time you plug in, you're getting the final velocity at that moment. So my y value will actually be my most current or my final velocity. Hopefully we remember that the slope of a velocity time graph gives me acceleration, so I'll replace m with a for acceleration. The x variable is time, and the y-intercept is actually the initial velocity. So y actually represents like the current y value at whatever x value you plug in, also known as the final velocity at any given time you're trying to analyze. So if I just take slope-intercept form and I just plug in what the variables actually are, I get this equation here. The final velocity of an object is equal to the initial velocity it was traveling at plus its acceleration times the time that it was traveling for. And this is actually the first kinematic equation. You can see we have an equation that relates initial final velocity as well as acceleration and time. This equation won't technically give me anything about displacement, but I can solve for any of the other kinematic variables. That one's the most straightforward one. The second one is a little more complicated, so I'm going to walk you through it. Again, you don't necessarily need to write all of this down. You don't need to be able to necessarily do this from a graph. I won't give you a graph and say derive me the kinematic equations, but I think it's important to understand that they came from these very concepts that we've just learned. So just to show you the second one, it goes off of the idea that the displacement from a velocity time graph is the area underneath that velocity time graph. So if we look up here, we should hopefully realize that if I want the displacement of this object, I need to find an area, and I have two distinct shapes, the area of this rectangle and the area of this triangle. So all I've done down here is just written, well, that displacement is really the base times height of this rectangle, and 1/2 the base times the height for this triangle. I'm going to do the same thing I just did, but I'm going to plug in the values that are actually there. The base of this rectangle, the base is actually time, and the height over here is the initial velocity. So base times height actually becomes initial velocity times time, because the base is measuring time and the height is measuring that initial velocity. 1/2 times the base times the height of the triangle translate to, well, 1/2 the base is still time. And you can see down here that the height is actually the difference. This whole thing here is final velocity. I have to subtract out this little piece because the initial velocity is here. So this whole piece right here is actually the whole final velocity minus whatever my initial velocity was. So when I plug that in, I wind up getting this delta x equals VIT plus 1/2 times VF minus VI times T. Again, you don't necessarily need to be able to do this, but hopefully you're following along. I've calculated the area, and I've just substituted in these values. Now I have to do a little bit of algebra. All I did in this next step was distribute the time. So instead of saying 1/2 and then in parentheses VF minus VIT, I've just distributed. So I get VIT plus 1/2 VFT minus 1/2 VIT. I've distributed the time as well as the 1/2. Hopefully you see I have VIT here and VIT. So VIT minus 1/2 VIT will give me 1/2 VIT plus the remaining 1/2 VFT. Again, I'm going to assume that that last sentence probably sounded like a foreign language to you. You don't need to be able to do this. Please just understand that. I just want you, if you can, to follow along to understand where these come from. All I have to do here now is I can now pull out that 1/2 and pull out the t and wind up with delta x equals 1/2 in parentheses vi plus vf t. As you can see, these can get complicated in terms of how we derive them. These are two of the easier ones to derive, so at least it gives you some appreciation as to how difficult it was to piece all of this together. And the fact that we have 5 equations that have been derived for us, at least we can now appreciate the work that went into actually generating those. If you derive all of them, you actually wind up with what are known as the kinematic equations. This one here should look familiar, as should this first one. I've provided the other 3 for you as well. So aside from the 2 we derived, you also have the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. The displacement equals the initial velocity times the time plus 1/2 at squared. And the displacement is also equal to the final velocity times the time minus 1/2 at squared. The reason why there are 5 of them is because each of these equations is missing one of the 5 kinematic variables. Remember, the kinematic variables are initial and final velocity, acceleration, time, and displacement. So this first equation has 4 of the 5, but it's missing displacement. This second equation is missing time. The third equation is missing final velocity, the fourth acceleration, and the fifth initial velocity. So if I'm provided some kind of example or some kind of problem, and I'm not given any displacement information, I have no displacement, this is the equation I should be using. If the next problem I'm given information and I'm not given anything about its final velocity, well, this equation does not have final velocity, so I can use this equation to relate the other variables. You can copy these down. I also have linked in Google Classroom. You should have the link to the kinematic equation sheet. It's also a useful resource as well. So you can write these down or you can just use that sheet. I'd like to quickly just go through 2 examples to show you that the actual application of the kinematic equations are not that difficult. Yes, the derivation is a little insane, but once you have these 5 and you understand at least where they came from, the application of these equations is fairly straightforward. So we'll look at this example. You have a car starting from rest. It's going to accelerate at positive 1.5 meters per second squared. And I want to know how long, what time will it take to go 100 meters? So how long, starting from rest, accelerating at 1.5 meters per second squared, will it take this car to go 100 meters? We have never had a problem in this class yet where we've related acceleration and displacement, but we now have equations we can use to do so. The most important thing is to always list what you know. We know the initial velocity, we know the acceleration, and the displacement, where we don't know time. The variable we're missing that we're given no information about is final velocity. Yes, we're looking for time, so we don't technically have it, but velocity, the final velocity was not mentioned at all. So we need to go up to our kinematic equations and find the one that in no way is reliant on final velocity. And I get delta x equals VIT plus 1/2 AT squared. I'll take that equation and plug in what I know. 100 equals 0 times time, so that just goes away because 0 times anything is 0, plus 1/2 the acceleration times time squared. If I multiply both sides by 2, the 1/2 goes away, this becomes 200. Divide both sides by 1.5, I get 133.33 equals t squared. Square root of both sides, and I find that it will take this car exactly 11.54 seconds to accelerate at this rate from rest and go 100 meters. I now have an ability or a way to relate acceleration, velocity, and displacement, and time. I can relate all of these variables in one. Looking at one more example, we have an object that's already moving to begin with. It's traveling at 3 meters per second in the forward direction. It's accelerating at 1 meter per second squared, And I'd like to know how far will it have traveled by the time it accelerates to positive 6 meters per second squared. So essentially, how far will it go in order to have accelerated from 3 meters per second to 6 meters per second? If we take a look, I list what I know. Initial velocity is positive 3, final velocity positive 6. Acceleration positive 1 meters per second squared. I am looking for displacement, but I do not in any way have any mention of time. So I have 3 that I know, 1 I'm looking for. I don't need time. If you know 3 of these 5 variables, you can always find everything else. So I don't have any time, so I'll come back up to my equations. There's only one equation that is not reliant on time. If I choose these other ones, I'll run into an issue. They require time, and I don't have it. So I'll use the one equation in which I don't need to know time. Vf squared equals Vi squared plus 2a delta x, and plug in what I know. 6 squared equals 3 squared plus 2 times 1 times delta x. 36 equals 9 plus 2 times delta x. Subtract 9 from both sides. 27 equals 2 times delta x. Divide both sides by 2. And this person would have taken 13.5 meters to accelerate up to its final velocity of 6 meters per second. So the way these are all applied are by figuring out exactly what variable you're missing, choosing the appropriate equation, and then just plugging in the values you have and solving for your unknown. It's not incredibly difficult, especially when you're just analyzing one object. It might be a little more difficult when you have to compare two, but that's something we'll look at later. For now, you should be able to apply these kinematic equations to the example problems for one object moving in one dimension.